Van der Graaf's classification presents varying figures for the number, density and thickness of the Earth's internal layers. However, in contrast to his model, most of the geoscientists follow a widely accepted universal scheme which divides the internal structure of the Earth into three primary layers based on composition and the physical properties. These layers are lithosphere. The lithosphere is the outermost solid layer of the Earth which is composed mainly of granitic rocks. It has a thickness of about 100 kilometers and contains high concentrations of silica and aluminium. The average density of this layer is approximately 3.5 grams per cubic centimeter, and the second layer stands for pyrosphere, which is lying beneath the lithosphere. The pyrosphere consists primarily of basaltic rocks. This layer extends to a depth of about 2780 kilometers. It is denser than the lithosphere with an average density of around 5.6 grams per cubic centimeter, and the third layer is barysphere. The barysphere represents the innermost part of the Earth and includes the core. It is mainly composed of heavy metals like iron and nickel. This layer extends for nearly 200 kilometers to the core. The average density of this layer ranges between 8 to 11 grams per cubic centimeter, making it the densest of all the layers. Seismological evidence will play a significant role in identifying the internal structure of the Earth. Let us see those evidences. A seismograph is an instrument that records earthquake vibrations, and the graphical output it produces is known as a seismogram. Seismograms help us to understand the nature, type and strength of earthquake tremors, which are mainly resulting from the motion of tectonic plates. The Earth's crust is divided into large sections consisting of 7 major and the several minor plates, which include both oceanic as well as the continental types. Seismic waves generated during earthquakes are mainly divided into two types: body waves and surface waves based on their motion and the medium through which they travel. So, first one is body waves, which propagate through the interior layers of the Earth, and they are further classified into two types, that is primary waves, which known as P waves, and the secondary waves, which is known as the S waves. Primary waves. These are the fastest seismic waves traveling at speed of approximately 5 kilometers per second, and these are compressional or longitudinal waves that move in a push-pull manner parallel to the direction of wave propagation. The motion of P waves is similar to the vibrations in a sitar string. So, where air is compressed and rarefied to produce sound. So, P waves can travel through all three states of matter, that is solids, liquids and gases, because these media resist changes in volume when subjected to compression and quickly return to their original state once the stress is removed. These waves travel slower than the P waves at speeds of around 3 kilometers per second and move in a transverse direction, that is perpendicular to the wave propagation or wave motion. These waves cause shearing vibrations, changing the shape rather than the volume of the material through which they pass. An everyday analogy to understand S waves is to take a soft garden hose that is about 2.5 meters long and fix one end to a vertical pole and shake the free and producing a wave motion along the length of the hose, so that you can understand what is S waves, isn't it? So, unlike the P waves, S waves cannot travel through fluids, that is liquids or the gases, as these materials lack the shear strength to support such deformation. This important character will help us to know the information about the interior of the earth. Surface waves. These waves travel alongside the earth's crust and cause the utmost damage during earthquakes due to their high amplitude and complex motion. They move slower than body waves but have a greater impact on the surface. Again, these have been classified into relay waves, which roll like the ocean waves, and the love waves, which cause the ground to move horizontally from side to side. Exploring Earth's interior is difficult as light cannot pass through, and drilling is limited to about 12.5 kilometers due to extreme heat and pressure. Instead, scientists use seismic waves from earthquakes recorded by the seismographs to study underground layers, much like doctors use scan to look inside the body. So, seismic waves reflect, refract or diffract as they pass through different materials. These changes reveal boundaries, depth and rock properties. For instance, wave bounce at new layers and bend when materials change and curve as speed increases with depth. Faster wave speeds in denser, harder rocks help scientists determine the composition, temperature and state of Earth's interior without direct access. Based on insights from seismology, the interior of the Earth is categorized into three principal concentric layers. The first one is crust. The crust is the outermost solid layer of the Earth. It is where we live and carry out all our daily activities like building houses, farming and running industries. For example, the studio I am recording here, isn't it? It is situated on the plain, which is also a part of the crust. The crust includes all landforms such as mountains, valleys, plains, rivers and forests. It is also covered by a layer of air called the atmosphere. The thickness of the Earth's crust is not the same everywhere. It is thicker on continents and thinner under oceans. On average, the crust is about 20 to 40 kilometers thick based on its location. So, the continental crust can be as thick as 70 kilometers in mountain regions like the Himalayas, while the oceanic crust is much thinner, about 5 to 10 kilometers. The crust is made up of two main layers, that is the outer crust as well as the inner crust. The outer crust is also known as the Sia layer because it is rich in silica and aluminium. This layer is composed of three primary types of rocks. Those are igneous, sedimentary and the metamorphic, with granite being the most common. The Sia layer is thicker on land and has a density of about 2.7 to 2.8. Below the Sia is the inner crust, also called the Sima layer, and this layer has more silica and magnesium and is made mostly of basalt rock. It is thicker under oceans and has a higher density of about 3.0. So, the boundary which separates the outer and the inner crust is known as the Conrad discontinuity, which is named after the scientist Conrad, who discovered it by studying how earthquake, that is seismic waves, change behavior at that particular point. Seismic waves provide important information about the Earth's interior, as we discussed earlier also, isn't it? So, these waves move faster in denser material. For example, seismic waves travel at about 6.1 km per second in the CR layer, but their speed increases to about 7.9 kilometers per second in the CMA layer. This shows that wave speed increases with density. So, these changes in speed help scientists to study the different layers of the earth.